concept of isolated system in every physical theory. Okay, so unable to do that will result in the result that otherwise we have to太大了哈。好，这个，哈哈哈哈哈。那这样，好 ，OK。So, unable to do that will have the following result. Otherwise, every time one has to consider every detail of your physical system. So having a notion of isolated system will allow you to break a physical system into small parts, study them individually, then you can combine them together. One has to consider every part of the system. And he concludes that we were unable to make any progress. Okay, so and the notion of isolated system can be found in Newtonian gravity. Okay, so in Newtonian gravity, we have the physics is governed by this Poisson equation, where rho is the mass density and phi is the gravitational field. So basically, for an isolated system, we mean that rho is 0 outside outside a complex set. And the boundary condition for phi is that phi goes to 0 as r goes to 0. However, in GR, so suppose we want to get a similar concept in GR. First of all, we have our Minkowski spacetime. It's the spacetime where there is no gravitational field. Right? No. Okay. Therefore, an isolated system, the concept of an isolated system is equivalent to finding a suitable notion of asymptotically flatness, meaning that you have to describe how the Lorentz manifold approach R31 in a suitable sense. So isolated system is equivalent to definition flatness. And so, and actually for physicists, so there are, so not unlike our mathematician, there are no correct or incorrect definitions. Just more or less useful ones. Yes, useful ones. Okay. So at spatial infinity, from the study of positive mass theorem, now mathematicians have, at least mathematicians have a good understanding of what is asymptotic flatness at spatial infinities. Maybe thanks to Shen Yao's work and Barnick-Crucial. But for non-infinity, it's not that clear. And here we just present one approach. Yeah. Sure.
Are you looking for Newtonian gravity? It goes to zero, so R goes to infinity.
Oh, infinite. Yeah. Yes, R goes to infinity. Okay. Yeah. Thanks. Okay. And so, as Mudol mentioned in the morning, so Penrose's idea actually comes from a geometric one. So we can consider what happens. So take this example in Riemannian geometry. So for hyperbolic plane, if you look for a textbook definition, usually it's this. Okay, so in a three-dimensional Minkowski space, you look for a hyperboloid. Okay, so this is the easiest definition for beginners because you can draw analog to spheres in Euclidean space. And however, and you take the induced metric of Minkowski. You take the induced Minkowski metric on this to be the Riemannian to be the hyperbolic metric. Okay, but this is in fact not very easy to work with. So what's next is to show that this metric minus. Yeah, I think that's a confusion. Yeah. So what's next is that you do a stereographic projection with respect to this 0, 0, -1. Okay, and then this projects the hyperboloid into a unit disk. Okay, so this is then isometric to the unit disk in R2 with a metric equals to 4, 1 minus x squared minus y squared dx squared plus dy squared. Okay, so now the picture is this. So hyperbolic metric is nothing but Euclidean metric with a conformal factor, and of course hyperbolic space is non-compact, and while this one is a finite region, but as you can see, the conformal factor goes to infinity as you approach the boundary. So okay, so this guy is actually non-compact, and this picture is very helpful for visualization, for we can view the boundary of the unit disk as points at infinity of hyperbolic plane. Okay. And also, conformal change, of course, preserves the angle. So, for example, you can draw the geodesic on this the so-called Poincare disk easily, and see their behavior. Right? These are the geodesic for the hyperbolic space. So Penrose's idea is similar to the treatment here. And one last word before I give you the definition. So in his notes, when he say fields, he means tensor fields. Okay. And he also uses the so-called abstract index notation. Okay, so this means that, for example, when we study Riemannian geometry, we will study vector fields and one forms. So you always read such a sentence: let Y be a vector field, or omega be a one form, say on a manifold. And we will take local coordinates to do computation. On some local coordinates, we can write Y in components, say YA partial XA, and omega equals omega A dXA. So usually when we think of index upstairs, we know that we are dealing with vector fields, or more generally, control variant tensor fields. And when we see an index downstairs, we know that we are dealing with forms, or more generally, covariant tensor. Okay. So so if you have YAB, this is called the contravariant tensor field. This is covariant. And for physicists, to save notation, they tend to not write all these. Just consider YA or omega A. So when you see this, you know that now we have a vector, and here we have a one form. Okay, this A you don't put a numeric value into this. This is just a symbol. We have a vector or a one form. Okay, and sometimes I'll also use this abstract index notation. Okay. Now here's Penrose's definition. Let M tilde G tilde be a spacetime. And it's a symptote. Mg, or sometimes it's called the unphysical spacetime, is so this is a manifold with boundary I, and there is diffeomorphism from M tilde to M mod I such that G is equal to omega tilde G tilde, and at I omega equals 0. So, or more precise, the zero set of omega equals 0. But d omega is not 0 there, but d omega is null covector. Okay. So this is his definition. Let me give you an example. For Schwarzschild spacetime, the metric G tilde is -1 - 2n over r dt squared plus d phi squared. So if we make a change of coordinate, let u equals t minus r minus 2m log r minus 2m, and x equals 1 over r, then we can write this as x to the negative 2 du dx minus x squared 1 minus 2mx du squared plus d theta. Okay.
Find the node of the d omega is equal to 0. Is this
Yeah, this G is
only at I?
yeah, only at I. This condition only hold at I.
You assume E will equal to 0.
No, so you can, so in Lorentzian geometry you can have a non-zero vector that has zero length.
D omega is like.
Yes, yeah, that means yeah. So this d omega is a non-zero null covector. Yeah.
The covariance is with respect to the
You can replace this by partial, so so there's no ambiguity here. Of course, we have to be careful which covariant derivative we are using.
so the one with tilde is
The physical one.
the physical one.
Yeah. Since he will mostly work with the unphysical one, so this one is on tilde in Penrose theory. So this is also called unphysical. Space-time. So for Schwarzschild, you can take omega to be x, and this to be g. So g equals omega squared times g tilde, and this x equals 0 corresponds to r equals infinity. And the picture looks like this. Okay, so this represents a three-dimensional solid. Okay, but we want but the space-time is four-dimensional. Therefore, each cross-section here is actually a two-dimensional sphere. Okay, we suppress one dimension and draw the four-dimensional space-time as a three-dimensional solid. And okay, so I forgot to say that. So this last requirement tells us that I is a null hypersurface. So, for example, here you have a null vector here, d over du. This on the boundary of unphysical space-time. And okay, the spacetime is not arbitrary. We impose the Einstein equation. Okay, so okay, so let me denote this normalization by SAB, the Ricci tensor minus 1/6 GAB. Okay. Using this SAB, we can decompose the Riemann curvature tensor as CD plus GACS minus GBCSDA. Okay, and here the bracket means that we are doing an anti-symmetrization. So this is the notation. And for parentheses, it means symmetrization. And the Einstein equation that we are going to use is, so maybe let me write it here. Omega SAB plus 2 MB minus FGAB equals omega inverse LAB. So here, the one form NB is just the shorthand for d omega, and F is inverse. And LAB equals and LAB equals GACLBC. Okay. So here I won't derive the. So okay. So. Sorry, this formula is just the conformal change of Ricci curvature tensor, and writing it this way. And in my talk, I will always impose the Einstein equation. So we assume that the Ricci tensor for the physical spacetime is 0, and so this is 0 here. Okay, and this is. So I will refer to this as the Einstein equations in my lecture. And you note that, okay, here we already assume a certain regularity at infinity. So this guy is 0 by the definition here.
Why is the LB 1/6?
1/6.
LAB is the Einstein tensor, the physical space.
Not exactly Einstein tensor.
Oh.
I think
You're assuming LAB is equal to 0 for the physical one.
yeah, for the physical one. The Ricci curvature for the unphysical spacetime may not be 0.
Kill that one. You're assuming LAB is equal to 0. I thought you were.
Yeah, LAB is maybe it's better that I put a tilde here. Is that more clear?
Ricci.
Yeah. So we start with a vacuum.
Your physical space.
That is vacuum.
It's vacuum.
Yeah.
Oh, you're assuming you. Okay.
Yeah.
So R tilde AB is equal to 0.
Equals 0. Yeah.
So therefore LAB is also equal to 0.
Yes. Yeah. Of course, in the lecture note, Garrosh is very careful with this. He doesn't impose the vacuum Einstein equation, and in every theorem he has to assume some decay assumption on this LAB, and then you can have corresponding theorems. But for convenience, we assume that LAB equals 0 from the beginning. Okay, so from the definition, we know that this guy is 0, right? But we impose certain regularity so that when multiplied by omega inverse, this f is still smooth at infinity. So in other words, we at least assume it's the unphysical spacetime is C1 at infinity. Okay. The gauge freedom in this formalism is that you can choose the conformal factor arbitrarily. So you can choose a different conformal factor which is related to the original one by a positive function. And for later reference, we note that after the conformal change, the NA is G prime. I'll compute this later. Is omega inverse n upper A plus omega to -2 omega nabla A omega, and F prime equals omega inverse F plus 2 omega to -2 and m omega plus -3 omega. Okay. So for example, the first one, NA prime is G prime AB nabla B omega prime. So this is omega to the -2 G upper AB. So G prime AB equals omega prime square G tilde AB is equal to omega square GAB, and nabla B omega, capital omega. So expanding this, we get omega to the -2 omega GAB omega plus omega inverse GAB blah B omega. So this is n upper A, and this n upper A. So we get the desired transformation for formula. And the formula for F prime can be derived similarly. So now we'd like to define this strip I, some copy of I.
That's not, they're not both same thing. The first one is the two terms. You write them as both equal to NA.
Oh, so yeah, sorry. This is nabla A omega. Thank you. No, we consider this diffeomorphism. And this script I is viewed as the now infinity, but now infinity. Okay, from M. Okay, so we like consider this script I as an abstract manifold, and using this zeta to pull back all information from M to script I. So first, so from the definition, there's no problem to pull back all covariant tensors. Yeah. Pull back. Covariant. So tensors with lower indices. Okay. For M. And for example, we get for functions, for example, this is omega circle, and this is because omega is 0 on I, so we get that this guy is 0 on script I, and suppose this one also gives you 0 because this is theta star d omega d omega 0. Okay, so this one form NA pulls back to 0 under zeta, and more generally. Covariant tensor has a pullback being 0 if and only if it is the sum of tensor product of covectors such that at least one of them is a multiple of NA, at least one. Okay, so this can be checked. But it's more difficult to pull back contravariant tensor. Okay. So first we isolated this class, script C. Let script C be the tensor field satisfying this criterion. So it turns out that zeta star is only well defined on this class script C. Okay, so you can check that for tensor fields in this this class, we can it is so zeta star is well defined. C. The definition is however indirect. So we define this through this relation. So suppose this term is non-zero, then you divide this factor to the left-hand side to get this guy. Okay. And you can check that alpha being script C is the condition to make this well defined. Okay. Okay. We can.
Thank you.
So let me give you some characterization of this class C. Vector is in C if and only if it is tangent to I. Okay, so you can only pull back these you can only pull back tangent vectors for a 1-1 tensor to be in script C. It has to satisfy if you contract it with this one form n, you also you get a multiple of n I, and or if and only if this is tangent to I for any tangent to I. Okay, so this should not be hard to see. So from the definition, okay, so suppose you are given a vector and you check this condition for any new satisfying this, right? But we know that essentially the only one form satisfy this condition is the multiple of n. Therefore, so mu a, and so this means that for proof of 1, so mu a in C if and only if mu a n a equals 0, and if and only if mu omega, so mu a equals mu a nabla a omega equals 0. I mean that mu is tangent to the level set omega, which is I. And for the second one, so this is in C, so so you have to again you contract with n lower b, that the result has to again be 0. Therefore it has to be a multiple of n. The only thing that is annihilated by a zeta star. And this can be seen to be equivalent to the later completion. M? Yeah, he used M and N as index also.
A, B, C, and you suddenly jump to M.
Yeah, A, B, C, D, and M, N, P, Q, and that's the index he will use. Yeah, so it's not surprising that you will see this later. Yeah. Or maybe he avoids this, but we have to be careful. Yeah, using his coordinate system, his index system. I think he's careful, not not to see that you will only see like NN.
Yeah, but what
I don't know. I don't know.
Not, I mean, there's nothing special about this indexes, right? I mean,
No.
To me, just like ABC.
Yeah, just yeah.
He likes it.
Yeah. A, B, C, D, E, F. Yeah, you cannot use F because F has a special meaning. So F also not G, right? G, H. Why? Yeah, H has some meaning later. So I guess he can only jump to N. Okay, and okay, there's some other interesting property. Which is in some sense very counterintuitive. So this zeta star commutes with some tensor product. These are not surprising. But unfortunately, it doesn't commute with contraction. Okay. An example is that if you pull back the identity endomorphism, so this is in the 4-dimensional spacetime, you can check that you'll get the identity endomorphism on a 3-dimensional manifold. And when you take trace, that this gives you 4 and this is 3. Okay. And in general, the contraction of tensors in class C is not in C. Contraction. Is not in C. One example is this. So we have LA, LB, and C. So this L is the vector that is L is the unique null vector. LA is the null vector. Complement to N with LA NA equals 1. Okay. So this 2-1 tensor is in C. So if you contract this, okay, and then you will end up with something with n lower C, and you pull back this is 0, okay. But if you take trace of this, for example, if you trace A and C, you get LB, and this vector is not tangent to I. Okay. So this is the direction of L. Okay. So yeah, so usually we have to be careful when we apply the usual operation to tensors here. However, he mentions that if an index annihilate this one form N, then you can contract this part. Then this makes sense, and the usual formula holds. So you can then this pullback zeta star commutes with contraction. the last property we need is that this zeta star can commute with Lie derivative. We have a vector tensor in C, then the Lie derivative in the direction of K is again in C, and we have that it commutes with. Okay, so this is another property that we will use later. Now we define two fields on script I. So first, we pull back. Okay. So because this vector is null, so we can pull back this to get a vector field on script I called n bar, and we can also pull. So this is okay. We can pull back all covariant tensor. We call this G bar. So here's some proposition. So and so since this is 0, right? And you can write it as G, A, B, and B. So we get G bar A, B, N bar B is 0. So in other words, this G bar is degenerate. Okay? This is and but otherwise it's positive definite. So the signature is 0 plus plus. So we will have a degenerate metric on script I. And the second one is we can pull back the Einstein equation. So here we have an omega, so this term is 0, and we get 2. And this term, since this is an exact one form, so this guy is actually the Lie derivative of the metric. Okay, so we can pull back these two terms to get L n bar G bar equals F bar G bar, where F bar is the pullback of F. So in some sense, this n bar is a conformal Killing vector field for G bar. And finally, so we also have to understand the behavior of n bar and G bar under the gauge transformation. The result is, okay, so n bar prime equals omega bar, and G bar prime AB equals omega bar. Here, omega bar is the pullback of the additional conformal factor. So from this last proposition, we see that this gamma A, B, C, D equals n bar A, n bar B, G bar C, D is gauge invariant. Okay, so the factor cancel. Okay. And actually, he mentions a proposition that all properties of n bar and G bar can be written in terms of gamma A, B, C, D. Okay. So yeah, so he gives some hint to this, but I'm not able to verify that. So I just maybe give you a sample of these how this can be done. For example, there are basically here. So G bar annihilates N bar, and it has signature 0 plus plus. The conformal Killing property, and yeah, so basically there are these four. So for example, the first one is equivalent to gamma AM CM equals 0. Okay, so maybe I should. Okay, so maybe the first one is gamma A B C D equals gamma A B C D and non-zero, and gamma A B C D gamma E F G H equals 0. Okay, so he claims that these two properties ensures that this 2-2 tensor can be decomposed into n bar A, n bar B, G bar C, D for some n bar A and G bar C, D. And then the first property will be equivalent to gamma A and B and equals 0. And you can also write the second and the third property in terms of gamma.
So what is this statement? This statement said, suppose you have gamma that satisfies symmetry.
Yeah.
And then you can
actually find the vector field and the symmetric 2 tensor decomposing this. Yeah. And then this property, okay, so after you find this decomposition, this will tell you that the n bar and g bar you get will satisfy n bar A, G bar A, B equals 0. Yeah, something like that.
Can you give an indication of what you want to achieve today?
Oh, okay. So it appears in the next definition. So because all the property of this field can be written in terms of this gauge invariant 2-2 tensor, so he will call I gamma A, B, C, D is called an asymptotic geometry. Okay, so now his starting point is a three-dimensional manifold with a 2-2 tensor that satisfy certain properties so that you can extract an n bar and g bar from it. And then he starts working on that.
So this is a three manifold.
Yeah, a three manifold.
This symmetry.
Yeah, and this 2-2 tensor satisfies certain conditions so that you can.
So AB is AB symmetric.
AB symmetric, CD symmetric.
And then you have this quadratic expression.
Yeah, you have this and other property equivalent to 2 and 3. So you can extract from this gamma n bar and g bar satisfying these three properties. So actually, every time we will get this n bar, g bar to work with, but not with this gauge invariant 2-2 tensor.
So this is just a three manifold.
Yeah.
With a tensor that satisfies
Some properties.
These two properties.
There are more. There's another one equivalent to 2 and another one equivalent to 3, but written in terms of gamma only. I think it will be more clear if I write them down. Okay. The others are longer. So, for example, here. C, V, A, gamma, B, C, D, E. Implies that so this property is equivalent to signature. Yeah, for any WV with this non-zero, this function is positive. Yeah. And finally, there is this one, V, A, gamma, B, C, D, E equals 0, implies that LV gamma is a function of gamma, and this is equivalent to the conformal Keeling property. Ln bar G bar equals some function beta G bar.
That's all.
Yeah.
Gamma. How many
Yeah.
of them?
How many? 3.
But in terms of gamma, which three? I can really say.
Oh, okay. So the full definition is that this is called the asymptotic geometry if this gamma satisfy this 1, 2, 3, 4, 5 properties. Yeah. 5 properties. Yeah. And from this pair, you can get n bar and g bar satisfying these 3. Wait, just 3. These 3 properties.
And how unique are this pair? I mean, eventually you should swap NA and GAD.
Yeah, it's not unique because this gamma is gauge invariant,
Yeah.
but n bar and g bar are not.
Yeah.
So there's this freedom.
possibility,
Yeah,
or-
yeah,
So they only differ by a positive function.
yeah,
Divided by I.
yeah. Yeah, I didn't check this statement. So, but yeah, but he claims that, yeah, this is what you can do. Yeah. So this term this definition will be gauge invariant. But yeah, but of course the n bar and g bar you get is gauge invariant. And in fact we will use this gauge behavior to normalize them later. For example, the first one we will make is this. So here we have the relation of f under conformal change. So if we pull back this equation by zeta star, okay, so we have, so say f bar is zeta star f, then we get f bar prime equals omega bar inverse f bar plus 2 omega bar to a negative 2 n bar n n omega bar. The last term is 0 because we have omega there. And from here, you see that the right-hand side is omega to the, so for example, so this term is just, so maybe we can write this as omega bar inverse f bar plus 2 n bar log omega bar. So we know that if we choose this conformal factor omega so that omega bar is satisfy the ODE that omega such that n bar log omega bar equals minus 1/2 f bar, then the resulting f bar prime will be 0. Okay, so we can choose a good gauge so that this f prime is 0, and in this gauge, from this conformal Killing equation, we get that Ln bar prime g bar prime equals 0. Okay. And this is the most useful gauge we will use later. And let me give it a name. Decomposition of gamma A, B, C, D is a choice of n bar A, G bar C, D such that gamma A, B, C, D equals n bar A and Ln bar G bar equals 0. Okay. And we know that this is a decomposition, not the decomposition, because we still have some gauge choice. So if you replace omega by tau omega such that n bar tau circle zeta equals 0. So suppose you multiply this omega by another factor tau such that this tau, when you restrict to I, is constant along the n bar integral curve. Then this omega bar would be replaced by log omega bar plus log tau bar, and the additional term is 0. Then you still get the decomposition. Okay. So yeah, so you know that even in a decomposition, we still have some gauge freedom to use. Okay. Finally, we like to define covariant derivative on script I. Define so here I make a jump. This definition is adopted from a later section. So actually he gives another definition of covariant derivative, but I find it more difficult to work with. So I take the later one. So okay. So the definition is this. So first we define how to covariant differentiate a one form. So given a one form here, mu b on script I, so we can extend it. Okay. So basically, this is one form living on script I or I, and you can extend it to a neighborhood of I. So you extend it to one form on M. So for some M, and so of course this extension is not unique. It's unique up to something like this. Because zeta star of MB is 0, so of course you can add an arbitrary multiple of it to nu. And because capital omega pulls back to 0, you can add a term like omega times an arbitrary one form to this nu. Okay. But you note that, however, the covariant derivative of this is, okay, this
What is tau b here?
tau be an arbitrary one form.
An
So
arbitrary one form.
yeah. So
It's just multiplied by omega.
yeah, just by a function that vanishes on I. Okay, so this nu is unique up to these two factors. Okay, and we note that this ambiguity is 0. So this ambiguity under covariant derivative is 0 under zeta star. Okay, so the first term is 0 because we have a lower b here, and the second and the third one is also 0. The fourth one is 0. For this one, we use the pullback of the Einstein equation. This term is 0. This term, if we choose a decomposition, okay, this by a decomposition we mean that the resulting f bar is 0. Okay, zeta star. So this goes to 0 if f bar is 0, and if we start with a decomposition.
Where do you use the Einstein equation so far?
To show that this part has pullback 0.
This part pullback 0.
Yeah.
What do you mean this part?
If we pull back this Einstein equation, this term is 0, so we get 2 zeta star.
You can just assume it.
Hmm?
Well, you can just assume. You can just make assumption.
Yeah.
I mean, is that true that so far everything that you've done, just make assumption that you have a conformal vector and you have your square is just a zero set of this omega.
Yeah. All from the definition and maybe the Einstein equation here. If this is not 0, then you will get a non-zero right-hand side. So this guy will not have a 0 pullback.
But I can assume, or can just assume this as a zero pullback.
Yeah. You can assume it's.
No, I just want to know the relevance of what you talk about. The relevance to Einstein equation. It doesn't seem to be. I mean, where do you use Einstein equation? I mean, I can of course just assume the term is equal to 0 without referring to Einstein equation.
But this is not obvious, right? You can choose this is the Hessian of the conformal factor.
Yeah.
And it's not obvious to me that you can choose a conformal factor whose Hessian is identically 0 at the boundary. This is not obvious.
I mean, it doesn't really use the Einstein equation in any essential way. I mean, you just have, a GAD and NA and you make this assumption. I mean, for this asymptotic geometry, it doesn't really use any Einstein equation, right, for this to be.
But I need this fact to define a well-defined covariant derivative. So the problem is that this G bar, we'd like to view this as a metric on script I, but it's non-degenerate. So we cannot use what we learned in Riemannian geometry to define a covariant derivative. A degenerate, yeah. So it doesn't associate to a covariant derivative naturally. But we still want to do covariant differentiation.
Yeah, but I mean, I just don't see the relevance to Einstein equation so far. I mean, you write down this equation, but really you're not really using the whole equation, right? I mean, so far you just deal with GAB and you have this.
But they satisfy only when we in a vacuum space-time we know that the right-hand side is 0. Otherwise, you have a source.
What would be a more non-trivial example?
Non-trivial example. Of course. For example,
it's trivial, right?
Yeah.
I mean,
you have. Okay, so maybe, for example, if you are in a space-time satisfying the Einstein-Maxwell equation, you can show that the resulting this L will come from the energy momentum tensor of the electric magnetic field, and you can show that this will still approaches 0 at a suitable rate. So that when you pull back this relation, you still get 0 on the left-hand side. But of course, here it just looks like a technical assumption that we have to really impose a vacuum Einstein equation. It doesn't have to.
The first term is equal to 0, and the third term is equal to 0. Only the middle term is now 0.
Yeah, but we still have this term, right? Zeta star. So you have to assume that your stress tensor approaches 0 at a fast enough rate. Maybe this is what you. So for example, I think so. He mentions that all his theorem holds if this LAB approaches 0 faster than O to the omega to the 4. So yeah, indeed, we don't have to be in a vacuum spacetime as long as your stress tensor approaches 0 at a faster enough rate.
You could have a more non-trivial example.
More non-trivial.
Vacuum.
A non-vacuum example.
Vacuum example.
Vacuum example. I think. Sure. And for example, any spacetime with boundary size coordinate can be put into this formalism, right? So, but if you were here last Tuesday, then you know what boundary size coordinate is. So it's like minus 1 minus 2m over r du squared plus some lower the term plus 2. So given a G tilde like this, you can pull out this R square, right? Like in Schwarzschild. And so again, this is omega to the -2. If omega equals r to the -1, you have minus omega squared. Is this what you would like?
But in this case, the metric is just a standard one.
Yeah, it's the standard one. Yeah.
And
Yeah.
the NA is just the DDU direction.
Yes.
Yeah, but
Yeah.
I mean, but what's the point of?
Here, of course, the strip I doesn't have to be S2 cross R. We haven't imposed any topological condition, so it can be any surface direct sum with an interval. So optimal, yeah. So optimal it's quite quite general. So and we should say that so far everything is universal. You don't really see the G tilde AB. The G tilde AB will appear in the next lecture. So yeah. So I'll comment on this later. So now the upshot is that, okay, so now this additional term will have 0 covariant derivative under the pullback. Therefore, it makes sense to define covariant derivative dA mu B equals zeta star. So picking an arbitrary extension. Okay. And using this definition, and then, so after you know how to differentiate one form, you extend this by requiring that zeta commutes with some tensor product, and so then you can some product. Then you can differentiate an arbitrary covariant tensor field. And requiring it to commute with contraction, you can, for example, define the covariant derivative of, for example, you can define it for all contravariant tensor. Okay. So we can covariant differentiate tensor fields. And also from it, you can check easily that the A G bar BC equals zeta star, nabla A G BC, which is 0. And also, this N bar is parallel. Say we test it with a one form to get partial A bar B bar B minus bar B. This is the pullback of NB nabla A U B. This is pullback of nabla A and B U B. Okay, but we know that under decomposition, this guy vanishes at I, so this guy is 0. Okay. How much more time can I have? 5, just 5 minutes. Okay, so then let me finish section 4. Okay, so I'll postpone the discussion of BMS algebra to the next lecture. Okay. So say we let this B, called the base space, to be maximally extended integral curve. Bar. Okay, so this is a set of curves, and we can define a projection map from strip I to B. Okay, so given a point, you send it to the curve that passes through it, and so the picture is like this. So, there's a lemma saying that to characterize the tensor field that comes from a come from a tensor field on B, the condition is mu. B, if and only if it satisfies mu. So a tensor field on script I comes from a tensor field on this space B if and only if it any index contract with n bar you get 0, and the Lie derivative of this contravariant tensor is 0. Suppose we now have, we are working with the decomposition. Suppose n bar A, G bar C, D decomposition. Then we know that G bar satisfied, this is automatically satisfied, and this is also. And we have G bar AB equals pi star HAB. And the second, and this HAB will be positive definite. And moreover, so for any one form on script I that comes from B, we have the covariant derivative is the pullback of the covariant derivative on B with respect to this Riemannian metric H. Okay. So this is one property. And we recall that even in a decomposition, we have a gauge freedom. Okay, so two decompositions positions are related by omega bar satisfying n bar by a conformal factor whose restriction on I is constant along the n bar integral curve. So this condition with the lemma tells you that this omega bar is the pullback of some function on B. So this implies that this translates to the gauge choice in this HAB. So we have you can change the metric conformally on this space. Okay, so it is in this sense. Everything we talk about today is universal. Everything. Okay. So it doesn't tell you much about the metric tensor. So the explanation goes as follows. So locally at, so suppose you pick suppose you pick a point here on I. Okay, so, and of course you get a point on script I. So taking a neighborhood, this is this is diffeomorphic to B cross some open set U cross, say U naught and U1, and this is an open set in B. Because any two-dimensional metric is locally conformally flat, you can choose this this conformal factor suitably, so that this H prime is flat, and so everything will look like the same. Okay, so in this sense that the construction so far just provides us a universal background, and the real physical property will come from the other property of G tilde. You have to do you have to pull back other fields to get something really different. Okay, so far everything is the same.
What do you mean everything is the same?
So everything. So I mean, so you can assume that this G bar, locally you can assume that this G bar is the pullback of a flat metric.
Two-dimensional.
Two-dimensional flat metric locally. Yeah. So for every G tilde, locally it looks the same. I mean the data n bar G bar associated to it are locally the same by choosing a suitable gauge, suitable conformal factor. Okay, so suppose we have M tilde 1, G tilde 1, M tilde 2, G tilde 2. Okay, and they satisfy the Penrose definition in that they have a conformal compactification. Then locally at their infinity, they are just the same. They are, so locally you can find the chart so that it looks like some open disk cross product with some interval, and this open disk is equipped with a flat metric. So you can, so locally you cannot distinguish these two.
But you have to go through all these to show that it's the same one.
He mentions an easier one. So in the middle we have this gamma A, B, C, D, right? So he says that you can choose a coordinate system so that gamma 1, 1, 2, 2 equals 1, gamma 1, 1, 3, 3 equals 1, and otherwise it's 0. So that may be a faster one. Yeah. Mm. And so my original plan is to go further to the next section, which talks about the symmetry in this formalism, and the symmetry will also be universal. So therefore, even if you have a non-trivial space-time, you will have I should say okay. So locally everything is, so for example, locally everything is the same as what you will get from Minkowski space. So for everything we went over today, and it turns out that this R31 you can get the symmetry group of this conformal transformation, meaning that the gauge choice will give you will have infinite dimensional Lie algebra that is bigger than the Poincare algebra, and this one and the symmetry carries over to all a space-time with Penrose conformal compactification. Yeah, I'll stop here.
One quick question, or how do I ask at the class? So we will resume 10:30 tomorrow morning.